Thank you. Thank you. Thank you for having me here. And I'm so excited to be here because I have so many amazing stories to share with you. So I'm going to jump right in. But before telling you the stories, I want to take a moment to think of why we even need to tell these stories and celebrate these women that I want to talk about. And to do that, I guess let's first do a little activity. Because, it's evening and you need some bit of a warm-up. So I'd like to ask all of you to take out your phones, which I don't usually tell people to do in a talk, but just this one time, please take out your phones. We're going to do a little experiment because we're all scientists here. We love science. Those of you watching online, if you would like to also join, please do. It's a very, very simple experiment. I want you all just to do a quick Google search, and here's what you're going to do the search on. Just type in famous physicists and tell me what you see. I'm going to give you a moment. I've already done this ahead of time, just for the talk, of course. So I have my results ready to show you, but we'll take a time. I think we need a little music to get us through. Who's done the search? Hands. Okay, yeah, you're getting there. What are you seeing? Maybe I'll share with you what I'm seeing, unless anybody want to. Who do you see? Recognize any people? Yes? Who? Of course. Really? Einstein? No. Okay, yes. Well, here's what I saw when I did it. Kind of looks like what you're seeing, yes? Yeah, kind of. Yes, tell me. You have two. Tell me. Ooh, Galileo Galilei, and who did you say? Hawking, of course, absolutely. So I think these are definitely familiar names. But when I did the search, I noticed there was this little scrolling button, if you see right here. It shows these, so I scrolled. You guys can do that too. And this is what I saw. More faces. You might notice something if you scroll. Should I scroll some more? I think it's time to scroll a little bit more. Noticing something. True? Yeah, you can start counting maybe what you see in terms of how many men versus how many women. Do you notice any more that you recognize?
It's mostly all men.
Mostly all men.
While I checked, there was only Marie Curie.
Oh, really? You only saw Marie Curie? I think at least there's Curie, and she's fantastic, but you're right. I think we're noticing a pattern here. I'm going to scroll one more time because I think there's one more page. And I kept hoping, this page will be different. This page will be different. Unfortunately not. So, the thing is, Google actually has it wrong. When we talk about famous physicists, you think about people who've literally transformed our understanding of the universe. And yes, these men absolutely have done that, but guess what? There's a whole secret history of women's contributions, and Google perhaps needs to do a little bit better. In fact, if you notice, there's also I noticed there's a little feedback button there. Maybe we should all click on it. Let's tell Google to do better. In fact, it's not just Google that gets it wrong. I think it's not just online. All of us also don't necessarily know these stories, right? Maybe we can help Google fix it. Does anybody want to suggest some names to Google? At least in that list of famous physicists, you'd expect that Google should suggest all the Nobel-winning women, at least in physics. Actually, Google does not list them. Do you want to help? Anybody want to suggest the? Yeah. Donna Strickland, our very own Donna Strickland, absolutely. She doesn't figure in that list. Did she come up in anybody's lists? Isn't that amazing? In fact, sadly, I have even more sad news for you. I remember back in 2018 when Donna Strickland actually won the Nobel Prize right here in Waterloo. There was a lot of celebration. I was so excited, so proud. You know, the third woman in history to win the Nobel Prize in physics, first Canadian woman. So I figured, wow, this is going to make her a household name. Well, a few months later, CBC ran a poll and asked Canadians to name a woman scientist. In any field, not just physics. Literally, maybe 4 or 5 months after Donna Strickland won the Nobel Prize. And half of Canadians couldn't name anyone, leave alone Donna Strickland. So this is what's happening when Google deletes women, when we don't pay attention to these kinds of news stories. We are perpetuating a history that's not complete. And it's not just about acknowledging fairly all of these women's contributions, including Donna's. It's also about how that impacts the next generation of scientists, those who are working today as well as in the future. So I want to show you one more slide before I tell you all these stories that I have. This is an amazing slide. It's got so much information, and I know it's really hard to read it all. I don't want you to read it all. I mean, I'm happy to talk more about it later if you're interested, but you can also look this up online. This actually shows you all the countries around the world divided by region, and it tells you what's the percentage of women researchers in STEM. So the black circle, the outer circle, the colored parts show you all the regions. The next circle, which is the black circle, is supposed to be showing 50% of women out of all of the researchers in that country. So if the colored bars for each, the vertical bars that are going out like rays, sun rays, if those reach that black circle, it means that there's 50% women in that country. And if it goes beyond, then there's more than 50%. And I think this is really amazing because packed into this little circle, you see the gap, literally the gender gap. And that's what's happening because we have this ongoing problem of acknowledging women's work and not understanding what we're losing by not celebrating that work. So I hope to address some of that by sharing with you some of the stories to prove that it's not just about, we should be inclusive because that's the right thing to do. It's to show you that the kind of work we're talking about is so amazing that not knowing it is just wrong. And it does impact how much science needs these kinds of contributions. So with that, I actually had a problem because when I was writing this book about these women, there were so many stories that I actually didn't know which ones to leave out. I mean, you can't put all of them in there. That's how many we're talking about. So for me, the way I went about collecting the stories and building, the chapters in the book was actually to try to relate it to the stories that I felt most deeply connected personally as a woman scientist myself. So I wanted to present it to you in that way so that you kind of can connect to it and try to see it perhaps through my eyes, just because there's so many stories and I had to find some way of limiting what I could talk about. So personally, I was actually born and raised in India. Grew up there, went to school there until I was about 16. So I want to show you some photos of my schools in India. So this beautiful picture on the left is my primary school. It's a public school in South India, Hyderabad Public School. The other one beside it, I went to after that for a few years before I moved. And I thought everybody's school looks like this for many years. These are great, amazing places. But the reason I want to show you this also is that if you notice there's the pictures of the flags up there. These are 4 flags at this school that I went to. It's in Kolkata, the city, Calcutta if you like. Back in British times, they called it Calcutta. Now we call it Kolkata in India, in West Bengal. And that school, we were divided into these 4 houses, with these colors, like different colors for each house and different names for each house. So basically, my childhood was exactly like Harry Potter's. Gryffindor and Ravenclaw. No, so the houses unfortunately didn't have the cool names like in the Harry Potter books. The house that I belonged to was actually this yellow one. There is a point to the story. I'll get to it as soon as I can. But a good story needs a good build-up. So there you go. The yellow flag, the name of my house, was Macaulay House. Why Macaulay House in India? Well, remember, this is the whole idea of houses and things like this comes from, British colonial times. And Macaulay was named after Lord Macaulay. And he happened to be the person who is acknowledged to have reformed Indian education. And what that actually means is that he believed strongly that Indian knowledge was not worth really much, and English education, educating all Indians in English, would be much better because there's more knowledge to be had, and that if everybody was, if there was enough education in English in India, the language I mean, then that would create a great workforce. That would be the administrative workforce in India to help the British manage India. So there you have it. That's what Macaulay's education reform was all about. And even till today, he is celebrated as the education reformer. So maybe now we also have to email, the Indian embassies and so on to tell them to update what they're doing. So anyway, that's Macaulay. Now, it all sounds, kind of like a bad thing that I'm telling you, but actually there's a silver lining. Because of that focus on English education, there were wealthy families in India at the time who could afford that kind of English education. And that's the connection. Lord Macaulay's effort to build this working class that would help to efficiently run the British Empire actually led to educating some incredible scientists in India. And the one I want to tell you about, her name is Bibha Chowdhuri, and I feel personally connected to her because she's Bengali like me. So she was born and brought up in Kolkata, where I too went to school, in that beautiful building at Macaulay House. She wasn't in the same school though, but she was in a well-known school not very far from my school. And so she got this English education. Her family was actually part of this Hindu reform movement called the Brahmo Samaj. And they really focused on women's education. So she got her degree in physics, just like I did many, many years later, of course. And this was back in, as I said, back before, in the early 1930s when she was, a student, and then she graduated and decided that she wants to continue doing research in physics. Not a lot of options back then, of course, especially because, as I said, there's not a lot of focus in the British Empire to build out science education in India. All of the focus on education was absolutely about, as I said, creating this administrative system. So in spite of that, she actually got admission to this university in Kolkata, which actually had already a track record of contribution in physics, because one of the professors there happened to be Professor C.V. Raman. And the physicists here will know that name very well. He is famous for something called the Raman effect, which won him the Nobel Prize, in fact. And he was the first, I believe the first Asian ever to win a physics Nobel Prize. And that discovery was done despite not having any funding from the British colonial administration at the time. It was all locally funded by local Indians with enough funds to provide for a chair for Professor Raman. So that's the university that Bibha Chowdhuri joined, because there's already a track record. She was inspired. She continued her physics research. And eventually, she ended up focusing on this new technique back then, which looked at trying to detect particles in the atmosphere that were created because of cosmic rays that were hitting the upper atmosphere and creating these particles that you can't actually see because they're far too small. But there was this new technique where you can take these special chemicals and coat them on these glass plates, and if you get them just right, these emulsions they're called, then you can actually detect these particles. Now, she didn't invent this technique. In fact, the technique itself was invented by yet another woman, Surprise, surprise. Her name is Marietta Blau, and she was actually an Austrian woman, a scientist, who maybe about a couple of decades before Bibha Chowdhuri also got her degree in Europe under very different circumstances, of course, worked at the Radium Institute, where she's the one who actually, by studying all the different chemicals that you can coat these plates with, was able to tweak things to the point where you can actually detect these particles and then also distinguish between a particle like protons versus some heavier nuclei and things like this. And keep in mind, before this, the only way to detect these particles was this other method called the cloud chamber method, which was, in fact, not as efficient, and it's not like you had a record of the tracks of these particles, whereas if you have a photograph, literally, you can look at it, and then you can do measurements, and then you can understand something about these particles. So Marietta Blau literally created that whole technique, and very soon, the whole physics community started getting very interested in this. All of the big scientists of the time realized, oh, this is a way to start really looking at particles and detecting what's happening, what's inside subatomic level interactions. So this was literally the moment when modern particle physics started. This is what Marietta Blau created. And she and her colleague, this woman named Hertha Wambacher, who was actually Blau's PhD student, they worked together and they basically wrote the book on how to use this photographic method to detect particles. And they actually became very well acknowledged at the time. And they won this very famous prize in Austria, which was kind of like their Nobel Prize at the time. 2 women winning this top prize of the country. Never been done before, and actually has never been repeated. So this is the level at which she was working. And because of all that work, the word spread. Actually, it was C.V. Raman who actually took some of these plates back to India to try to study these. And then Bibha Chowdhuri and her mentor, her supervisor to some extent, but they really worked as colleagues, this other researcher named Devendra Mohan Bose, they also got hold of some of these plates and decided to do some experiments. So they would go up to the top of mountains in India and try to record these tracks of particles. As you can see, this hazy picture is kind of like what they would see. And so just from these little, almost like ant footprints, you can look at the spacing of the tracks, and you can look at, the slight curvatures of the tracks, actually, and try to figure out something about the particles that make the tracks. And in fact, it was Chowdhury and Bose who realized that, some of the tracks, which seemed to be like proton tracks, actually kind of seemed to not be going as straight as they were supposed to, based on the calculations for protons. So they thought, well, this is a bit of a curvature. And so by looking at that and calculating things, they realized, the curvature says something about the particle. It's not quite as heavy as a proton, meaning it has as much mass as a proton, but it's not as light as an electron either. It's somewhere in the middle, a middle mass particle. They called it a mesotron. These days we call it mesons for middle mass kind of particle. But they couldn't quite confirm it, yet they wrote a bunch of papers, right? They published a series of papers, not just in local Indian papers, they all went to Nature. So Bibha Chowdhuri published this series of 4 articles in Nature about this new technique that she was developing to try to understand the mass of particles, and also pointing out that there is perhaps this new particle, this meson, that had never been seen before. Problem is, keep in mind, this was in the early 1940s. The war happened, so at the time, because India was still under British rule, India was also officially in the war. So all of the funding efforts focused on the war. So there was no funding for her to continue to do this work. So she actually abandoned it and decided to move on and do a PhD, but not in India. She actually went to the UK to do a PhD, which already is pretty impressive for her to be able to get into not just any lab. She went and worked in the lab of Patrick Blackett, who eventually became a Nobel Prize-winning physicist himself. So that kind of put all of that work on hold, and yet, after the war, because her work was published in all of these big articles, the technique was known. So during the war, and after the war particularly, this other group in the UK, led by a researcher named Cecil Powell, actually decided to continue that work, use the technique, but use better photographic plates to get better data. And this researcher, Powell, actually hired a whole group of women who would go and look at the data to try to calculate these paths. And they were called, I think, his name was Cecil Powell, so they were called Cecil's Beauty Chorus. Yeah, you can't make up this stuff. So, yes, the chorus, in fact, did find something amazing. They used that same technique that Chowdhury had developed and were able to confirm that, indeed, there was this new particle. And they confirmed this. The particle was called the pi meson, or pion, as we now call it. And it was really, really a huge discovery. Why? Because it was actually predicted to exist based on some theory that had been developed actually 10 years before that. And that theory was trying to explain what are the forces that hold a nucleus together. And in that strong force theory that was developed by this researcher in Japan, actually, called Hideki Yukawa, his theory actually predicted the existence of this particle called the pion, but back then, he didn't have the means to discover anything like this. But when Powell discovered it, that was huge. It was a big, big news. And in fact, that led to, in a few years, so this was in 1947 that the discovery was announced. In 1950, Cecil Powell won the Nobel Prize for that discovery of the pion, but there was, of course, no mention of either Marietta Blau. In fact, Powell, his nomination said, for the development of the photographic method and the discovery of the pion. So this is unfortunately a trend that you will hear over and over in some of these other stories where the credit for some of this work that women have done, not only is it deleted, but the credit is actually transferred to the men that they either worked with or were working on similar things with. It's such a common thing that it has its own name. It's called the Matilda effect, which is actually named after the woman who named it. So yes, the women noticed. The men somehow don't necessarily always notice. And also keep in mind that Yukawa also won a Nobel Prize a year before that. So all the men involved did get a lot of recognition, rightly so. These were really amazing contributions. But there's more to the story, and I think that you don't lessen the contributions of the men by also celebrating the contributions of the women. So this was really sad for me because not only was Chowdhury not acknowledged back in her time, but she, by the way, is not mentioned in any of the textbooks that I studied, even in India, growing up. As a Bengali student in Bengal, never heard of Bibha Chowdhury until much later when I really started thinking about these kinds of questions. So that's a real loss, and I hope, again, maybe now I have to write to my school and say, could you please change your textbooks around this? So she's, to me, really somebody, as I said, because of my own background, I related to her. I did look up, the rest of her life story. I don't have time to get into all of the details, but I do encourage you to look her up because she had an incredible career, even after this. She went on to actually be involved in the discovery of yet another fundamental particle. We are actually bombarded by particles from the sun, and some of those particles are these things called neutrinos that are really hard to detect. And she was part of this huge effort where you had to go deep underground into a gold mine in India just to detect these particles because that will shield all the other particles. And so she was involved in that, and they did find the solar neutrinos. So it's not just one, but two fundamental particles that she has been involved in the discovery of. And she was also the first woman to be hired at the premier Indian physics institute called the Tata Institute. So she had an incredible career. But by the time she retired and moved on to doing other activities, and then by the time of her death, she was actually completely forgotten. which is quite sad. But I don't want to dwell on sad stories, so I want to move on to tell you about some other interesting stories. Again, this is perhaps more familiar to some of you. So, for my graduate student work, again, as I said, I'll tell you the stories from my own perspective. For my graduate student work, I actually was in New Mexico in the US. So New Mexico is such a beautiful state, right? So here's some photos from White Sands National Park and Shiprock, New Mexico. And they're both really amazing places. I loved the nature there. I actually got married in White Sands National Park. It's just wonderful. It looks like it's snow, but it's actually just beautiful sand, so nice and warm. And Shiprock is this huge rock formation, right, in the middle of just flat, empty space. Wonderful. It's actually on Navajo territory. I think it should be called Spaceship Rock. Because look at it, isn't it looking like it's just going to fly directly up some kind of a space cruiser? And in fact, the Navajo name for this formation, actually, I think it translates to rock with wings. So maybe they were thinking about spaceships too. But the reason I bring up space is because New Mexico is definitely played a huge role in the space program, and both these locations did actually. So the very, very early tests of, the very first rocket tests were done at White Sands testing range. And these were actually rockets that were brought over from Germany right after the war, because they were basically repurposed missiles. Because in Germany, of course, at the time, during the war, there was actually a very, very advanced rocket program led by this man who you may have heard of, Wernher von Braun. So have people heard of von Braun's name? Yeah. So von Braun, after the war, he also was brought over from Germany to the US. And of course, during the war, he led this effort. He was absolutely registered a Nazi party member. He was a member of the SS. He claimed that he was, officially not really a supporter. There's evidence that, questions his claims, but we won't go into that because the story that I want to tell you is not about von Braun. The story is about this amazing woman named Joyce Neighbors. And Joyce Neighbors was the first woman to hold a technical position in von Braun's team in the US when they started developing, the space program, which of course von Braun was actually leading that program. And keep in mind, this was back when there was that space race happening between the Soviets, who also, by the way, took half of the German technology. So both the US space program and the Soviet space program were both actually driven by German technology. So they were, in a sense, competing with themselves. Of course, on the Soviet side, they had a big win because they were the first to put a satellite in orbit. Anybody know the name? Of course, right? So this is part of the history we do learn. Sputnik was the first satellite in space, so the Americans were running to catch up. And the first American mission was, anybody know that name? After Sputnik, the year after that, since it was back in 1958. I'm hearing some whispers. It was Explorer 1. We are explorers, yay. So yes, Explorer 1 was the mission, and Joyce Neighbors played a major role in it. She actually had a math degree and a physics minor, and then she went on to do engineering. She had all the degrees. Not back then, that was early in her career, but she led this team who were tasked with calculating the highest point of the trajectory once the rocket was launched. And at that point is when the secondary stage rockets had to fire, because that's what would put the satellite into orbit. And if you get that wrong, you either are flying off or you're coming straight back down. So very, very important. Keep in mind, it was all done by hand, and there was no actual data because it was the first time. So you had to guess a lot in there. So that's the team that she led. Explorer 1 did launch, and it was a success. And so even though it was second to Sputnik, it was certainly a huge moment, a milestone in the US space program. And in fact, Neighbors' role was so important. Of course, she didn't get any coverage in the news. All of that went to von Braun and some of the other leaders, who were all men, of course, at the time. But within the actual team, her role was deemed to be so important that she was given this special honor. That's what's shown in that paper there. She had this special honor that she was asked to sign the mission chart as as a way of recognizing her. Just her and von Braun and this one other scientist were asked to sign it. So it was really a big deal, given the many, many, many people who worked on these kinds of missions. So she did sign it, but if you notice, if you squint really hard, I don't know if you can tell, it says A.K. Neighbors, Alice K. Neighbors. Alice was her first name, but she went with Joyce. But she explicitly did not write her full name. She was told not to, because a woman's name would actually undermine the authenticity of the chart. She chose not to actually, fight that. She agreed not to sign only her initials. Von Braun, on the other hand, an ex-Nazi party member, could sign his full name. Just saying. Seems kind of relevant these days to tell these stories again, given what's happening. So Joyce Neighbors, again, yet another woman who then went on to have an incredible, a stellar career in NASA, where she worked on so many projects. She worked on Skylab, which was before the space station. That was the project that led to the space station. She worked on, experiments that were about testing general relativity. Then after she retired from NASA, she went on to Lockheed Martin and continued working on space-related projects, and had quite an impact. And throughout her career, she was always constantly having to justify her position and her role. So whenever there were cuts at NASA, she was brought in and said, your husband has a good job. You don't need to earn anything. So maybe you should, it's your duty to give up your spot to a man who would need the money to help support his family. So this is the kind of thing that she had to hear and address. And she, at some point, told herself, I will fight like a tiger. I will not be going anywhere. And she did. For her entire career, she did. And she eventually was left alone. I guess people realized, okay, you can't get rid of her. So she did have this incredible career, and she fought for women's rights throughout her career, as many of the women in these stories did, because they faced it so much themselves. The other person I do want to mention also, who was involved in this very, very major, huge effort, which was the Apollo program, the initial moon landings, was this woman named Mary Ross. I don't know if anybody's heard of Mary Ross. So she's, again, one of these incredible stories that I wish we celebrated more. She was actually from Oklahoma. She was born and raised in Oklahoma. She was from the Cherokee Nation. And she was, in fact, probably the first Cherokee scientist to ever be hired into the space program, because during the war, she decided to go and work for Lockheed Martin. And at the time, of course, there was not a space program, but she worked on this special projects group, very elite group, that was focused on, of course, developing warplanes for the war effort. And she was part of this group called Skunk Works, which is actually now well known and acknowledged as this elite R&D group. And so she was the only woman on that team, of course, and she worked on developing this aircraft called the P-38. And this was the workhorse of the US Air Force during the war, had thousands of missions, and it, in fact, was flown throughout the entire war. So that was her contribution during the war, and it was so important. Keep in mind that after the war, what happened was a lot of women who had joined, the Air Force, well, not the Air Force in terms of not flying as pilots, but helping as engineers and mathematicians and so on, just like her, were asked to go back and leave those jobs because the men came home. Lockheed actually noticed that she was so good and so talented that not only did they ask her to stay, they maintained her role in Skunk Works and actually paid for her to go and get even more education in aeronautics engineering. But she was interested in all that, but her secret dream was to actually explore spaceflight. So back when she was getting her education in mathematics, she discovered astronomy, and she took all the astronomy courses. And then when this opportunity to do aeronautics education happened, she did all of that. And then she was perfectly positioned when Lockheed Martin eventually became part of the companies that were involved in developing the US space program. And then she got to work on her dream, which was on this particular rocket called Agena. So Agena is not that famous of a rocket. People have heard of rockets like Saturn V, and they've heard of perhaps Atlas, the Atlas rockets. But Agena was a smaller rocket. It was a second-stage rocket. So Atlas Agena was this combination, where Atlas was the big one that would fire for the launch of many of these initial test launches, and then Agena would be the secondary stage rocket that would put, let's say, satellites in orbits or send probes to Venus or the moon and things like this. And it was very maneuverable. So it also acted like a spacecraft itself. So this is what she helped design, and her contribution was so huge that she was used for recruiting others and saying, she was celebrated by Lockheed Martin for all of her achievements. And Agena became the workhorse, just like P-38 was the war workhorse. Agena became the rocket workhorse for the space program, led to successful missions to the moon, to Mars, to Venus. Lots of satellites launched with Agena. And in fact, right here in Canada, anybody know what our first satellite was in space? Was it? Not quite. It was Alouette. Anybody remember Alouette? Yeah, that was launched using Agena. So we have a lot to thank Mary Ross for. She continued, of course, her whole entire career. She spent at Lockheed. She, after retirement, she too was very much involved in efforts to bring in more indigenous women and just indigenous scientists in general into not just the space program, but science in general. So that was another wonderful story that is related to the space program that we don't know. We've all heard of stories like Hidden Figures about the black women at NASA, but there's so much more. And I want to mention one more, which is related to Spaceship Rock, because there's another reason it should be called Spaceship Rock. Because back when the Apollo program was happening, NASA actually needed computers, right? Good computers that would be small enough to put into rockets. Keep in mind, this was back in the days of ENIAC, where computers were the size of a room. So when the first chips were developed, they would all, the circuits had to be actually connected by hand. And they had to all be designed, all the components had to be put in by hand. It was really tedious work. There was a factory built in Shiprock, New Mexico, on Navajo land, by this company called Fairchild. Fairchild actually was the company that eventually led to Intel and the whole Silicon Valley, right? So Fairchild built that factory there because there were no labor laws on the Navajo reservation, so you could get cheap labor. So it was almost entirely the women of the Navajo reservation that built these chips. And it was considered unskilled work because, apparently you and I can also do that. Just build chips if you need to. But you see, it's interesting because this picture looks a lot like, the carpets and the weaving, the Navajo tapestries that you might see. And in fact, that was part of why these chips built at the factory here had very low failure rates. So this is part of how the lunar program actually was successful, because this was such an important part of all of those efforts. And eventually, the workers there, actually, there was a riot because the working conditions were so bad that the workers rioted, so Fairchild shut down the factory and left. So unfortunately, not all stories have good endings, but I think it's time to recognize the kind of contributions that these women made to our space history. So before I end, I wanted to very quickly mention, because I'm a quantum scientist, so I want to talk about when I came to Waterloo, at the hub of quantum science and technology, all the exciting things happening here in Waterloo. In quantum, too, there are unrecognized stories. And some of them have to do with the very, very earliest kinds of contributions in quantum that are not celebrated. But I think perhaps we have to change all of our textbooks to make sure that we do, especially now that we're in this age of this new quantum revolution. I want to talk about old quantum science. In fact, this one woman who is well known perhaps in astronomy, but really, she was one of the early quantum scientists. Her name is Cecilia Payne-Gaposchkin. She did a PhD in Harvard, the first person to do a PhD in Harvard, where she was looking at the light from the sun, which you see here in an image where you see all these missing parts of the light. That's essentially because of light that's been absorbed by whatever are the gases on the surface of the sun. So by analyzing that, she figured out something incredible. And how did she analyze it? Well, back then, this was in the early 1920s, there were these equations that had been developed exactly to analyze this kind of situation. Actually, those equations were developed by an Indian scientist, guess what, from Kolkata again. His name was Meghnad Saha. And these are called the Saha ionization equations. And these are based on quantum theory, which was actually very early days of the theory. Not a lot of people knew enough about it to be using this work. So Cecilia Payne was aware of this, and so she took those equations and applied them to her analysis of the sun's spectrum. And she realized something. It's like, well, all of these stars have all these different sorts of, kind of these barcodes, if you like, the spectra. But if you actually apply the equations correctly, then she found that the star is basically made of only hydrogen and a little bit of helium. And that's true of all stars, actually. And she was able to show that this is a general principle. So essentially, she figured out what the entire universe was made of, because that's what it's in the stars. No big deal, right? That was just her PhD thesis. And it was actually quite a radical idea, because people thought that the sun should look a lot like the Earth, right? And Earth has lots of other things, not just hydrogen and helium. So there was a lot of skepticism, and she actually added a sentence in her thesis saying, the calculations are perhaps wrong. But she did get her PhD, but there was no role for her, and she basically worked without any faculty position at Harvard for over 10 years. Then eventually they said, okay, we'll give you the title of astronomer. So then, and she wrote all these incredible papers and articles, wrote the textbook on variable stars. And then about 20 years later, after this amazing PhD, they're like, fine, okay, you can be a professor at Harvard. So she was, not only did she become a professor, she became the chair of the astronomy department. And she was the first woman to be chair of any department at Harvard. So I think it's time to acknowledge her incredible contribution, because this is about, as I said, the whole universe, one of the most fundamental discoveries of what the universe is made of, and it comes from Cecilia Payne, who here already knew. I know some of you did know her story. So she is, I think, perhaps a little more celebrated in astronomy, but those of us who are in quantum science and technology, I hope you share her story too with all of your students and friends and so on. And not just her, I also want to mention another, perhaps out of all the women that I've talked about, perhaps the most well-known and well-celebrated is Wu Qianxun, because she actually did these incredible experiments that overturned something called, almost like one of the pillars of physics, which has to do with, I'm not going to go into the details, it's called parity conservation. And she did experiments, kind of like, if somebody said, well, there's something wrong with gravity, which of course, Einstein did go there. So it was at that level. She was able to overthrow a law of physics, what was considered a law of physics, through her experiments. So she had this huge impact on what we call now the standard model. But there's also this other, perhaps lesser-known contribution she made. She was the first person to do experiments which showed quantum entanglement between particles, where when let's say you have a particle and its antiparticle, when they annihilate, you get energy out, and these are particles of light called photons. And those photons are actually entangled, meaning they have some correlations and certain properties. So that's what she did. She did that experiment, and she measured those correlations, and she showed, yes, there's correlation. Now, to show full entanglement definitely needs more than what she did in her early experiments. But now, it is absolutely acknowledged that what she had measured was the first step in establishing the correlations of quantum entanglement. So she too should be celebrated in this area that I myself do research in, which is in quantum entanglement. So now whenever I look at any papers, or I'm thinking about my own work, I always make sure that I remember Wu Qianxing's contribution. By the way, none of her work, the parity violation experiments, which is known as the Wu experiment, or her entanglement experiments, none of that, of course, led to any kind of Nobel Prize. She did get other awards, but it was her colleagues, again, who got Nobel Prizes for these kinds of contributions. And she is absolutely recognized in the physics community, but her contribution is so huge that I think it's time to make her one of those names that Google actually lists, right? So I'll end with one more photo, which is taken when I was visiting the Kennedy Space Center, and I thought, well, there were all these huge signs of mankind and things like this. So I figured I would try to take a picture to perhaps send a message here. And I think we can all do that. I think we have this chance now more than ever. I think the women, when I went to the Kennedy Space Center, by the way, none of the stories that I told you, none of them were actually part of their exhibits or their displays. And you have to look really hard even to find the stories of people like Katherine Johnson, the hidden figures women who now are known. Even they were barely mentioned. And I guarantee you today, they're even less mentioned. They're being deleted today as we speak. So now more than ever, we need to speak up. We need to tell these stories. We need to shout it from the rooftops. Not to mention, they're kind of amazing and inspiring stories because they're about overcoming scientific challenges, but also overcoming all of these barriers, societal barriers. So again, I could only tell you the briefest sort of sketches of these women, and there's so many more. And there's so much more to the science they did. So I invite you to go and explore and find out more about these women and their stories and their science, and tell your friends and neighbors, of course, because in the end, it's not just about celebrating them. It's because if this is the level of contribution that women and anybody who's interested in science can make. It's science that needs women. And without it, I think we are all going to be poorer for it. So let's change the future. Thank you.
Thank you so much, Shohini, for that fantastic talk. All right, so now we have some time to take questions from those in the theater and anyone joining online. So if you have questions for Shohini, please make your way to the microphone that's located on the stairs. And if you're joining online, we have someone checking the online questions, and I will ask them here. While people are making their way to the microphone, I think I have one question for you, which is, so in researching these stories of these amazing women, what was that process like for you? Like, how did you, if many of these stories are missing from Google or sort of missing from textbooks even, how do you find out these stories? How do you kind of, do your research to get these amazing stories?
That's a great question. And I don't think that we can actually fully address this problem of finding those women, because you don't even know where to look. So for me, it's been a process over actually many years, because I've been teaching courses, of course, in physics for a long time. And so whenever I teach a topic, I try to go and perhaps look at papers, and then I look at references, and then references of references, then I look at footnotes. Some of these women, the work they did was they were not authors perhaps on papers, but sometimes they would be maybe an initial and a last name in a footnote. So sometimes you have to follow that trail, or accidentally you'll hear something perhaps mentioned by somebody in that field, and then you go and look at it. And then there's also archives you can look at. The universities actually do keep archives, and in Canada too, we are now building that archive. So those are some of the ways, but I think there must be so many other women that we have completely lost, because you can't hope to find them all.
Right. Yeah. All right, question from the audience.
So many years ago, I was working as an IT person and went to a physics party where the following conversation occurred. There's the wife of one of the physicists who said, physics is sexist. And all the physicists said, science is science. How can there be sexism in science? And she said, okay, so tell me how you teach thermodynamics. Well, you have an engine with a Carnot cycle. Okay, and what about hair dryers? What about hair dryers? Well, hair dryers are thermodynamics, just like engines. But you never use something that girls and women would think of. You always use a male kind of example. So using that as a background to this question is the problem that we hide women just because we can't see women and the value that they add, because what we choose to use as science, as men, is not what interests women, and what they choose to interest themselves in doesn't seem to be recognized. The science is the same, it's valid, but it doesn't get recognized. And so maybe the problem is at that fundamental level. We really need to re-examine what we look at and say, this is valued and it's the same, why aren't we seeing it? That would be an interesting question. And do you have a comment on that view?
Yeah, so personally, actually, I don't really use hair dryers much. I know it's hard to believe, but having all the hair. But I think that, I agree that we have to celebrate and identify applications of science in a much broader way. As in, there's science happening all around us. And some of the science we uplift and say, oh, this is important. And then other science we say, oh, that's not that important. And those kinds of judgments, you're right, are definitely about what society or whoever is the one making the decisions gets to say. And we have to question those assumptions. I think it's very unscientific to just have an opinion of what is important, what's not. One should be collecting some data and understanding how we make decisions. And that's, I think, a very valid point. I am a bit worried about trying to address the gender gap using gendered approaches. So by assuming that, oh, women should really be interested in physics because of hair dryers, and I've heard, of course, washing machine comes up a lot too, that actually also promotes gendered stereotypes of who women are and whether men versus women use hair dryers. So I think we have to be quite careful, because it becomes a slippery slope, and then we might end up inadvertently promoting stereotypes rather than addressing them.
Great question. Go ahead.
Thank you for your amazing talk. I just spent the entire time nodding and shaking my head, because I do a podcast where I talk about women who play guitars, and we found that, again, they're all around us, but we just don't talk about them. We don't celebrate their work. I wanted to ask, you had mentioned in your talk about the Matilda effect. And I just wondered, who was Matilda? And How did she realize this effect, and what should she have won a prize for?
Oh, so I should know more about Matilda herself. I do know that she was she researched behavior and she was able to identify this pattern. I don't know all of the details of how she came up with. I probably should. It's a fairly well-known effect if you talk to people who study behavior and decision making, as I was saying, and psychology. So I think she's well known there. It's not my field, unfortunately, but I invite everybody to go and maybe answer your question, do some research as well. But that's a good point. I think I should go look her up a little bit more.
One more quick question from the audience? Very quick.
Yeah, thank you very much. As a researcher, how much do we know? And how much do we still to know? We need to know in physics. Are there more for us to research than what we already know? Thank you.
Sorry, I couldn't.
How much in physics, how much do you feel like has been already discovered, and how much is there left to be discovered? How much do we know? How much is there left to be known?
Wow. How much time do we have?
Yeah, right. Unfortunately, we might have to leave it till after the
Yeah,
talk.
I think that's something also that'll take much longer to get to. Sorry.
No problem. Okay, well, thank you so much for our audience for your great questions and for your enthusiasm. And thank you again to Shohini. Let's give our speaker one more big round of applause.